What are we talking about when we say friction and string mass system? Okay, that is what we want to explore in this video. Thanks for coming back again. If you are a subscriber and if you're new here, endeavor to click on the subscribe button and turn on the notification bell. That will let you know when we drop a new video. So let's dive into what friction and string mass system is talking about. Okay, now in one of our previous video on friction class 1, we explained so many things about friction, and mind you, different questions that come after a topic used to bring up different discussions again, so or different ideas or different things to explain. So the basic principle and everything that applies on friction is what we have explained in the first friction video that was made. So now we want to explore another aspect that you might come across in terms of question that has to do with friction, and then this one is when you have a friction and string mass system. Okay, now before we proceed, I need to explain what is called a force called tension. Tension is a force that you can find in ropes. You can find tension in ropes when you hang a mass or you actually stretch the rope. Okay, I'm going to cite an example with this diagram. So let's say you have this is a string and then a mass is hung on the string. Good. Now don't forget the weight of this body, that's the mass. The weight is going to be the mass times gravity. So now let's say the weight is now a force. Mass is just quantity of matter in a body, so weight is actually the force that is acting downward. So which means the weight of this body is acting in this direction, and for every action there must be an equal and opposite reaction. But this reaction now would be given by the rope. It will be given by the what? By the rope. So this is the rope now, the string. Let me put it, the string. This is string. Oh, sorry. So this is string. This is the string. Now this is mass. Okay. This is mass. So now the mass have a weight W, which is acting downward in that pattern of arrow. Let's change the color of that arrow to red. So that makes sense. So now that is the direction of the weight, but there must be an equal and opposite reaction. Now the reaction is on the string. So the reaction will be in what direction? On the string. The reaction would be in this direction. In this direction. Yeah, that's the reaction. So this reaction is also a force, however might not be equal to the weight. So let's say it might be greater than the weight. Just like frictional force, when you're dragging an object, the frictional force might be greater than, the force you're using to drag the object might be greater than the frictional force. So it's fine. So then we can say that this force that is serving as a reaction on that string is not a normal reaction anyway, so it's called tension. So that's tension in the string. So even if the string is wavy or not stretched before, immediately you hang the mass, you discover that it's stretched up because of what? There is now a force T here called tension. Now what do we need all these to do? We need it in relationship with frictional force in set of diagrams I'm going to draw next. So now let's look at one typical example of the string mass system and their relationship with frictional force. So now let's get rid of this. Now I'm going to cite an example with an horizontal table. Now this is the table, and a block is a wooden block or metal block or whatever is placed on this table. So let the mass of the wooden block be small letter m. So this is small letter m. Then, okay, I think I have to shift it a bit. So let me shift it towards the side or at the center. So now, suppose I connect this mass with a string to another mass. Okay, so let's say at the edge of this table now, I have a pulley. I have a pulley that is attached there. Okay, let me say, yeah, a pulley. So then I have okay, let me try to draw the pulley system so we can get it well. Yeah, so this is very small. Okay, let me make this smaller. Okay, good. So I can bring this here. Oh, good. So now if I connect, let's believe this pulley is frictionless, so friction is not along the path of the pulley, a smooth pulley, you understand? So if it is a rough pulley, we need to consider the friction that will take place along the rope also. So now I hang another mass through the pulley, then connect the rope. So suppose I connect this rope or string. Okay, let's say the string is connected to the pulley in this manner. Okay, that way. Then I have the string extended, yeah, like this. So let's reduce the size of this. Yeah, okay, good. So then I connect a bigger mass. So let's say this is a bigger mass here, provided the mass is not touching the body of the table. So that is it. So let the mass of the big one be capital M. So now, what do you think will happen on this table? The big M will accelerate downward, and the acceleration of the big M will be the same acceleration for the small m. So which means the acceleration of the big M is downward. So A is directed downward. So the acceleration of this big mass is the same acceleration for the small mass. So the whole system is a string mass system. We can call this a string mass system. Okay, let me take it a little bit away from the diagram. So we call that string mass system. So that's it. So now what happens in this string mass system? You would see that the acceleration of the system is mostly calculated in most questions, like from A-level questions, UTME questions, WAEC or NECO, GCSE, whatever, NABTEB. They used to ask about the acceleration of the system. However, we can have any other question gotten out of this. So, but let's assume we want to talk about the acceleration of the mass of the masses. That's the system. So this is a string mass system with bigger mass hanged here. So now, what do you think will happen? So we are going to have a tension force acting on this string. So the tension force would be acting on the string like this. Yeah. So this is tension T on the string here, acting in opposite direction to the movement of big M. However, the movement of small m is this way. So then the tension will also act. We're going to have a tension T acting in this direction. Now, why is this tension acting in this direction? Yeah, because this tension that is caused as a result of mass M hang on the spring is dragging the mass small m from its position. So now dragging this mass small m from its position, don't forget mass small m is having the frictional force between the mass small m and the table. So which means the tension on the string is opposite the direction of the movement of m, but is in the same direction as the movement of small m. And this direction which it takes on the table, that's the tension, is in direction of the small m, but is against the frictional force, because frictional force is opposing its motion. So frictional force is going to be in this direction. Frictional force is going to be in this direction. So this is frictional force F. Good. So now with the way it is now, how do we calculate the acceleration of the system? So we are just going to discuss the formula here. So one thing is you need to analyze a lot of things here. Now you should know that force is mass times acceleration. So and the acceleration of mass m is the same thing as the acceleration of mass small m. So now how do we find the acceleration of mass big M? To find that, we all know force is mass times acceleration. Good. So if you now check, the total force acting on mass big M would be its weight and tension, because tension is acting in opposite direction. So which of these force is greater? If you look at it, if the tension is greater than M, so there is tendency that M will be driving up the table. But if M is greater than tension, that means the mass M will drive the mass on the table downward. So the way it is now, we would say since the mass M is bigger, that's the mass big M is big, so we can say that the weight of the mass big M is more than the tension. So don't forget the weight of big M, W, is what? The big M times gravity. So we have the weight big M, that's mg, minus tension. So this would be the net force acting on mass M, mass big M. So you must know the total force acting on it. So the total force acting on it is the difference between its weight and the tension. So and this force acting on it is equals to its mass big M times its acceleration. Good. Now let's take it back to the small m. So this small m, you can now calculate the acceleration of the small m. But for the small m now, you discover that the tension is greater than small m. That is why the mass m, the small m, can move in direction of the tension. It's moving in direction of the tension because the tension is a force greater than its weight and is dragging it. So then you can say tension minus, now what force are we going to subtract from the tension? Is it the weight of the mass m or what? We are not going to subtract the weight because it's not dragging it downward, it is actually sliding it. So sliding it, what force is opposing the motion to slide it? It is the frictional force. So we are going to subtract the friction, Fr, from the tension to give us the mass times the acceleration of the small mass. Now, the acceleration of the big mass and small mass is the same, just that their masses are different. So now, the frictional force, don't forget, coefficient of friction is the frictional force times normal reaction. So we can just say this is T minus coefficient of friction times normal reaction equals to MA. So at the end of the day, normal reaction would be mg, that's small m times g. If you want to if you want more explanation on why normal reaction is mg and all that, you can check the previous video on friction. So at the end of the day, we'll be having T minus this mg equals to ma. So these two equations that I'm going to be circling with or squaring with a rectangular box, a red rectangular box, are the set of formulas you can use to find the acceleration, as you can use them all together. So you, okay, that is the first one. So this is the second one here. Now this is the second one here. Yeah, these two formulas can be used to calculate the acceleration of the body. So you can check our Instagram page for questions on this, because we might not have time to solve a lot of questions. So then subscribe to our Instagram page at sar_logic. Then you check a lot of questions. So that Instagram page will be our question solving page. Okay. So now let's move on. Let's talk about, this is for a plane that is not inclined. So now the same thing implies on inclined plane, but just that, the formulas are different, because the mass on the table will be inclined at a particular angle. That is the case. So now let's check it out. Let's make a drawing for that. So we go, that is still on the string mass system, but don't worry, getting rid of it doesn't mean we have changed the topic. So now let's say the plane is now inclined. We're talking about inclined plane now, sorry, like the red ink, the black ink rather. So now the plane is inclined. So this is an inclined plane, and we have, okay, we want to talk about the spring mass system here as well. So the plane is inclined at a particular angle. Theta. So then, mind you, the mass is placed on it. So let's place the mass, small m, on it. Okay, good. So let's make the mass smaller so that we wouldn't have to stress ourselves much. Okay, good. So this is the system again. So we can say the mass here is big M as well. So why this is small m. So now this is the spring mass system on string mass rather on inclined plane. So what are those things that are involved here? Still using the basics of what we discussed in the previous video on friction, we would know that the weight of mass m, small m, okay, the weight of mass big M firstly, let's talk about that, is downward, and the acceleration is also in this direction. So definitely you have a tension on the string. So the tension on the string is in this direction. Good, that's the tension. Then this tension would also be in this direction. Yeah, in that direction, provided that the big M is dragging the system downward. So then we have tension T here and tension T here. So the formulas that we're going to apply here is the weight of this mass big M is mg. Good. So which is greater than the tension. So the acceleration still remain mg minus t equals to ma. So just like we did for the other one, but for this particular one, we are going to see the tension dragging the mass big M, small m, up the plane now. So the case apply to when we're talking about a force dragging the mass up the plane. Don't forget. So the force dragging the mass up the plane now is tension force. So since it's able to drag the mass up the plane, so the net force is going to be then tension. So that is gonna be, we are going to have a force that is taken to slide down to be mg sine theta as discussed in the previous video. Okay, so this is the force mg sine theta which the body takes to slide down, mg sine theta. So now, in order to slide to drive the body up, the force must be greater than mg sine theta. So which means we're going to be having tension minus mg sine theta is equals to ma. So these two formulas are used to find the acceleration of the system in this case. There are more complex cases that you can analyze as a result of the settings of the question. So then you can check our Instagram page at sir_logic to see questions on every topics done on our videos on YouTube here. So endeavor to do that. Thanks for coming. Endeavor to do that. Please subscribe to the channel. It's free. Thank you.